Well, last time we learned that when you want to get the electric field created by multiple point charges, it's just a matter of calculating the electric field created by each individual charge and then adding those vectors together. So it's a vector addition problem preceded by a little bit of some geometry in order to get this kq over r squared times r hat. And then you just vector add those together. It's the type of thing you do in Physics 1. It still applies here in Physics 2. But what I want to talk about in this video is what happens when you've got a charged shape. Like what happens when you've got a whole block of charge, a macroscopic charged object that's not a teeny tiny individual particle, but is an actual, shape with dimensions, with length, width, and height. What do you do with that? If you let's say you take a you take a rod here and you just charge the whole thing. You rip off a bunch of electrons or you add a bunch of extra electrons. What do you do there? Like, how do you add all of that charge together if it's just smeared out over the object? Well, the way you do this is you think about dividing up the object into teeny tiny pieces. So for example, here, I might think about taking this charged rod and dividing it up into a whole lot of smaller pieces. So I've got small positive chunks now. And what I can do is say that the total electric field at any point, right? Pick a point here. Say this is where we want the electric field. The total electric field there is just going to be the sum of all the electric fields for each individual chunk. So you take chunk 1, chunk 2, chunk 3, etc., etc. And there's kind of two ways to think about this. There's the mathematical way, and then there's the programming way. Let's talk about each of these. So for the mathematical way, what I'm thinking about is making each of these chunks really, really tiny. So I'm thinking about a small piece of charge, delta Q, located at each of these. Delta Q, delta Q, delta Q, etc., on and on down the line. And then what I want to think about is how far away my point is, the point I'm interested in, from each of these. So I've got this R vector going here for each chunk, and I've got a little bit of the electric field coming off of there. Let's color code that one red. And the thing is, I'm doing this for each chunk, so I'm thinking of this as being the delta E for that chunk, for this particular chunk. So delta E for the chunk, R for the chunk, and delta Q. We'll say that each delta Q is the same. Let's say we've made it nice and uniform, but you don't have to. You could make how much delta Q is a function of where it is in the shape. Maybe it's not a uniformly charged object. And so what you'd be doing here, you'd be taking the summation of each of these little delta E chunks, because you're making a small bit of electric field coming from that small bit of charge. So you're taking a summation of everybody's K times their delta Q divided by their R chunk, I'm going to get tired of writing chunk in a second here, squared, times their R hat chunk. Right? That's what you would be doing. You would be doing this over and over again. And the way to make it more accurate, the way to make this more accurate is to make the delta Q's smaller. So take even these 7 chunks we've got now and start dividing those up into more chunks. Right? Well, if you've been through calculus, you have an idea of where this is going. We're talking about taking the delta Q's and taking that into a limit of making those into dQ's. What's the difference between a delta and a d? The idea of a delta is that I'm taking a small slice that I can still see with my eye and say, there is the slice. The idea of the dq is taking that slice and making it really, really tiny to the point where I can't tell the difference from one slice to another. We call making it infinitesimally small. Well, when you take that limit, what you're doing in order to get this E total, you're turning this summation into an integral. Right? So when you take the limit of really, really small pieces, your summation is becoming an integral. Now, it's at this point, a lot of students feel this disengagement in their brain because they've been told for years that an integral is an area under a curve. And yes, an area under a curve is a type of integral, but not every integral is an area under a curve. Really what an integral is, at its most foundational definition, is that it's a summation of a lot of tiny pieces. The difference is, when you go from a summation to an integral, is you're making the tiny pieces infinitesimally tiny. It's still a summation. It's still adding up tiny bits. It's just you're making them so tiny that you can't tell where each piece begins and ends, and that means you get to use calculus instead of having to hard code, do all of this numerical summation by hand. And so what we end up with a K. We still have our delta Q now changing into a DQ. We've got our R squared. I'm going to stop writing the chunk because now it's just the vector R here. And then we have our R hat here. And so what the challenge becomes is, how do I integrate over all of this charge? Well, the way you do it, you need to change that dq into something you can actually integrate over, right? You never actually integrate over dq. That's just a symbol to stand in until we can figure out how it's related to something we can actually integrate over. So as I do this, what I think about is how, as I'm integrating over q, as I'm adding up all those tiny delta q's, I'm really going up and down. I should have made this go vertically, so we'll make it go vertically instead. What I'm really doing is starting at the bottom of that charged rod and moving up to the top. So I'm thinking about changing the y value. So each of my dq's is related to a dy, right? I want to think about how much charge each one of those little strips has. So one way I could do that would be to take the total amount of charge in the rod and divide it by the total length of the rod. So Q is going to be the rod's charge, and L is going to be the rod's length. Right? So Q over L is the amount of charge I have per length. So that's going to turn my dy, that is units of meters, into my dq, that is units of coulombs. And so I can take my E total, I can replace my dq like that. I've got my K, I've got my Q over L dy, and now I can think about my integral is going to go from 0 to L, right? Because what would you even put in for the integration bounds for dq? Well, there's not really anything you can put in there. We're just going to put in our 0 to L to go for our y bounds there. And then I want to start thinking about my R value here, right? I want to start thinking about what it is I'm doing with this distance that I've got going on right here. Well, when I think about it, that distance is a right triangle, right? So I am thinking about this in terms of my right triangle. And let's suppose we make this simple. Let's suppose we put our rod at x equals 0, just to make it simple, right? You get to pick where the origin is. And let's suppose we start here. We're going to start here at y equals 0. And so when I think about that, each of these distances is going to be basically our x value along here, and then our y minus y. Let's see, I want to think about this as being y minus y for the field minus y. So let's call it xf and yf. So we'll call this xf and yf for the x location of the field and the y location of the field. And so in that case, my distance is just x field squared plus yf minus y field, y field minus y squared. Oh, and then I got to think about this r hat business. Basically, for the r hat, I'm going to take, let's think about this. I want to take the position vector. So the position vector is going to be, that's going to be xf x hat plus yf minus y hat divided by square root, what's that going to be? Oh yeah, same thing I have over here. X field squared plus y field minus y squared. And so that's what's going to go in for r hat over here. You can tell it's getting a little bit messy, but it's the type of integral you can plug into Wolfram Alpha and have it spit out what the answer is. So if you want to do that, the way I recommend doing that is put it in once for the x component and then put it in again for the y component, because those are going to come out to be two different terms, and then you can have your electric field here. But if you're going to put it into Wolfram Alpha, we might as well put it into Python and get a numerical answer, right? So while you can integrate this, and it's fun to integrate this, and it's a worthwhile thing to look up on the internet and see somebody do, I like to go to the Python because then I can just do this numerically. So when we talk about doing this numerically, what we're going to talk about doing is going back to the original summation, right? Python can't really do this integral for you, but it can do the adding up the discrete delta q's for you. So how would you do that? Well, let's go back over to our code here from last time where we set up our or set up our dipole. Basically what I need is I need more charges. I need more charges to go along the direction of the rod that I'm interested in setting up. So let's start by getting these folks kind of on the same side here. Let's put them both at x equals 0. And let's put one at y equals -1 and one at y equals +1. And then we said we wanted to give these folks the same amount of charge. So let's suppose we put in a dq as q over L. And so what we're interested in is setting up what q is. Let's suppose we give the total charge a charge of 1 and the length, well, let's see, I'm going from -1 to 1, so I might as well make the length 2 and make those the two endpoints. And so what I could do now for my charge is just put in my dq. Right? Because remember our dq we figured out was going to be q over L times dy. And so I need to multiply by my dy here. So let's go dy equals our length divided by, let's say 2. Let's say we're doing our 2 points here, right? So I've got 2 of them. So my total length is just getting divided in half for each slice. So that is, so dy here is the size of each slice that we're putting in. So we'll run this now. Come back down here. We'll get our code to run here. And so what you get here is a point charge at 1 and a point charge at -1. And we're starting to see this charged rod take shape. It doesn't look all that much different from a point charge right now, because right now it's basically 2 point charges sitting right on top of each other. So not a whole lot different there. If I want to make this better, what I need to do is start putting in more points. Let's say we go from 2 points to 4 points, right? And so what I can do is take this one and copy, and let's paste it in here. And let's get a point that is, let's see, I need it to be about midway. So let's make this one a charge, let's put this one, at a y location of 0.5. Let's see, if I go from -1, -0.5, 0.5, and 1, I'm missing the 0, so I actually want to make 5 of these. So we're going to go from -1 to -0.5. Then we'll go from -0.5, copy, paste, to 0. And now I just need to get one more to go to +0.5. So now if I think about my charges, I've got one at -1, -0.5, 0, 0.5, and 1. Right? So I've got 5 charges now to represent my charged rod. And so I'm going to have to take the dy and take L divided by 5, because I've got 5 items in my list of charges here. All right, so we'll run that again to reset the charges. All right, let's see if our pattern changes a whole lot here. It changes a little bit. We're getting a little bit change in the direction of these middle pieces here. I think what we'll probably want to do is zoom in on this. I want to be able to get more of the, get closer into the charged rod there. So let's actually go back up here now and change our -10s to, let's say, 3s. Let's only go from -3 to 3 on each side. So I really want to zoom in on where the action's happening. Okay, cool. So now you notice we've gone from -3 to 3. Oh, I need to make that step size smaller. So let's go up here. I would like to get more of these. So instead of a step size of 1, let's make a step size of, let's go 0.2. I don't want to make the grid too overloaded, but this will give us a cool idea. Oh dear, I went too close. I went too close to 0. Yeah, you always want to avoid putting your field point right on top of your charge point, because you'll get a divide by 0 there. So let's go back up here. Oh, I know how to avoid this. We're just going to move let's just move the charged rod over a little bit. Let's make it at -0.1. There we go. So we'll put X at the X location here. If it seems like this process of changing all of these charges manually is a little bit tedious, we're going to make it untedious in just a minute. There we go. So what I hope you notice now is you can kind of see where the charged rod is, going from -2 to 2. And what I hope you notice is that the pattern's changing a little bit, right? Because for a point charge, the electric field lines go out radially. They go out in all directions. But if you look closer at just beside the rod here, you notice they're coming out parallel, right? Then what's happening there is all the vertical components from each of those slices is canceling, because one will be going up, its neighbor will be going down. Those cancel, and you only get a component going horizontally. And so we can make this more accurate by making more slices, but I'm not really interested in typing out all of those. So the way you can do that is by using a loop. So let's get an idea of how we would do this with a loop. The first thing I would do would be to create an empty list called charges. So here we're saying I want to create something called charges, but I don't want to put anything in just yet. Then what we need to do is loop over those y values. So we're going to say for y in range, in p.a range, and we're going to go from -1 up to 1 in steps of dy, right? We've already decided what our dy is up here. So this is going to go from -1 to 1 in those steps of dy. And then what we're going to do, we're going to call a charge equal to, let's just grab our dictionary here, copy and paste. So my q is still going to be dq. I still want that to be that nice uniform step that I've got there. My x is still going to be x. That's still going to be that constant -0.1. But now what I want my y to be variable. I want it to be this y that I'm moving up here. Now that's going to create that individual charge. So what I need to do is ask it to take charges and append to it the new charge. So append is a way you can tell Python that you want to take a list and add a new item to it. Let me show you what this ends up doing. Let's have this print charges for us. I'll show you what this ends up looking like. We'll run this code cell. See, charges ends up being another list of dictionaries. It ends up being another set of QXY, 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 and it's automatically generated these values for us. Now, oh, that's right. np.a range does not go up to the top value. So let me just put a 1.1 there. Python is funny sometimes. Sometimes it will do the top value and sometimes it won't. So if it ever doesn't, just put a little smidge on that top value, that maximum value, and then it will do, it'll go up to there for you. So we should get the same thing because I didn't change the number there. Now let's have it do more of these numbers. Now let's go from 5 to 20. Because now that I've got the computer doing it, I can have it loop over this however many times I want it to. And if you look at the list just got way longer because I've got more slices in the rod. I've taken the rod, I've now divided it up into smaller slices, which is going to make my electric field look better. It's going to look more accurate compared to the result you would get from doing the calculus, which is exactly what we get here. We get this kind of football shape here, because you notice that when you get close to the middle, you're just pointing outward kind of longitudinally this way. It's only when you get close to the edge here, to the tip, that you end up getting this, we call it a fringing effect, as it kind of spreads around that way. Let's see. Let's do a couple more things. Let's up this to 50. And I think should we put in a few more of these field lines? I think we should. Let's go every 0.17 instead of 0.2. That will give us a few more without completely breaking the display. Oh, except I got too close to those there. Okay, yeah, I got greedy. I should have kept those as 0.2. There we go. But what I would like to do now is see what happens when we make this DQ change depending on the, depending on where it is in the rod. Let's suppose, for example, instead of having the rod positive everywhere, what if I had a top half that was positive and a bottom half that was negative? How would we do that? I wanted to be able to flip the DQ. Well, one way I could do that would be to just ask it what the current value of y is, right? So if y is greater than 0, let's make it greater than or equal to, just in case we stumble upon 0. If y is greater than or equal to 0, then we're going to make DQ just stay the same. But otherwise, if y is less than 0, we're going to make DQ equal negative DQ. Oh wait, except I don't want to do that because that will permanently change DQ. So instead, let's do it this way. Let's have it take charge in here, and there it'll do the positive, and here it'll do the negative There we go. So in other words, if we're in the top half of the rod, we're going to make Q positive. If we're in the bottom half of the rod, we're going to make Q negative, right? So we have two different charges going on. And you can see that transition happen here. You've got negatives on the first half of the list. If you go all the way to the other half of the list, you've got Q's as positive numbers. All right, so this is going to make this top half positive, this bottom half negative. Alakazam. And there you go. You get a very cool pattern with electric field lines going out of the positive and into the negative. It looked a whole lot like the dipole we did before, right? This is now a physical dipole like you might have in an object, like you might have in a molecule or something, where you don't necessarily have a discrete positive and a discrete negative at two specific points. You've got it spread out. This is what that'll look like more in real life.